I am Dr. Fred Calef. I work at Propulsion Laboratory, and I serve many roles at JPL, but mainly I am like the keeper of the maps or the mapping specialist for a variety of the rover missions. So today I'm going to talk about how we're using mapping for Mars rovers specifically, but also just surface missions in general. So always have to have the rover land. It's very important. So you want to map Mars with rovers, and the question is like, how do you do that, and what's important? What do you need to know in terms of your location? So things you need to do, like you need to find a place that's safe to land from an engineering standpoint. You need to find a scientifically interesting place to land on Mars. You need to know where's the rover, how does it find out where it is, where do we collect surface data, and how do we plan where to drive the rover, right? So you've got this combination of working a spacecraft as well as understanding what scientific data is there, what you're going to collect, and what you can use to decide where to go to collect the data. And of course, maps are a very important part of that, which we use every day. So if you're not familiar with the rovers, now this is going to be a little bit NASA-centric, but here's kind of the family of rovers that have come out of JPL, from Sojourner from the late 90s to Spirit and Opportunity in the early 2000s to our current slate of rovers that I'll call a Curiosity class or MSL class. And you'll see in common 6 wheels. When we get to the later versions of the rovers, we have masts with instruments on them, and then we also have arms that we can then reach out to the surface and touch samples with other instruments, and even collect samples, or even put samples in tubes to return home. The latest mission, Perseverance, basically a Curiosity rover, but with different instruments. It is slightly bigger, but not in a way that you would notice. And importantly, we also have now, I like to call a subaerial platform, a Mars helicopter, which is only been a tech demo. However, has now done over 40 flights and is an amazing new platform in which we can do science. But as you can see, it's a lot of instruments, from different countries. And so we're talking about, a lot of instruments. You have to understand how they collect science and where they collect science, as well as dealing with a broad distributed science team, which is kind of the standard that we have. We have instruments coming from all over the world. We have people on the science team that are from all over the world, and we can't have everyone just come to one location and work from there. We have to eventually work remotely. So we start off with the science part. We look at Mars. We use various instruments like Prism and Omega to get chemistry of rocks and decide, and map those out and decide where we want to go from a science standpoint. But remember that we're going to be collecting data at 2 different scales, right? So we're going to have the orbital scale, which kind of gives us context, and then we'll have this very microscopic scale. And I like to use the phrase space to sand. So we get instruments that are in space that are showing us information on the surface, but then we also have data at the sand level, millimeters per pixel, little laser shots that are, hundreds of microns that we want to track, because now you're looking at stratigraphy at the centimeter scale, and maybe perhaps even at the millimeter scale. But we want to know where all those things are, so we can do things like this picture, which is combine instruments and take advantage of different wavelengths that they can look over, or just different capabilities to measure different elements, so that we can integrate that information together and come up with a new scientific discovery, or just collect data in a way that we hadn't before. So how do you deal with this on a mission? There's so many instruments, so much data, and so little time to do all these things. So oftentimes, like, we'll have a result. For example, like in the bottom left, we have like a laser-induced background spectrometer spectra. We go, oh, look at that. It's got really high manganese. And the very next question everyone asks is, where is it? And if you start to work these missions, you realize that where is it is not always an easy thing to answer. You can generically say, well, here's the rover, but then it's what rock is that on, near the rover? And then how did the laser point from ChemCam, where did that hit on that rock? So understanding the coordinate systems of mass and arms and doing the inverse kinematics of where an instrument is actually placed on a rock becomes a tricky thing, you know. So it's a lot of coordinate math, and not everyone has that knowledge. So we're trying to put that together so the scientist can ask the question, where is it? And we can just show them without them having to look at 10 different pages of wiki entries, right? And then work out all the math. So again, to find out where you want to go do a mission on Mars, you have to do engineering constraints. So here we're showing that based on our spacecraft, we have to stick within the bounds of from 30 degrees north, 30 degrees south latitude. And then we have scientific entry points in blue. And then we have things like areas that are too high to land because we just not enough atmosphere. So those are masked out in black. And then we have areas that are too dusty. Now for a nuclear powered mission, that doesn't matter per se. However, if dust covers everything, there's nothing to see without, you know, wiping off every rock. So in those gray areas are where it's too dusty. And so then we have this, you know, these colored areas, which are elevation, which are in between. And I'll talk a lot about Jezero crater and a little bit about Gale, the landing sites for the 2 rovers currently. Okay, so so really when we're doing mapping for missions, it starts with entry, descent, and landing. So we need to know where it's safe to land the rover. And so as it says in the lower left corner, we map all the things, right? So we start with the high resolution data we can get, currently high rise. From high rise stereo pairs, we can create orthophotos. From orthophotos, we can create elevation models. And also from the raw images, we can, from elevation models, we can generate slope maps. Also from the images, we can do machine learning to detect rocks, change that into rock abundance, and then combine all that stuff together, and you can make a cost map in terms of where you drive a rover, or just a hazard map of where you can land. So again, mapping pulls all those parts together, and that can feed forward into your mission. Changing over a bit to the science side. So before we landed in Jezero crater, much like Curiosity, we wanted to pull together a base map that the team could use and have some shared common knowledge of geography. As you see on the left here, we've named, you know, their names for the various valleys that come into Jezero crater, and then there are some key craters that were named or we added names to, and that gives us context. So we got the visual context. With that, you know, again, with stereo models, we get elevation data. We pull all that together into one layer or several layers, and then we can do the thing which we really want to do. And thank you, previous talker, for talking about XMARS mapping. We basically use actually the MMGIS software to do this distributed mapping. So we in the bottom left corner here, you can see how we divided the Jezero landing site into these quadrangles. They're actually like 1.2 by 1.2 kilometers on a side. And that was our basis for like about 40 team members to map a little section of the area. And then later, the bottom left is kind of like the uncombined version. And then later we would combine those and, you know, match up geologic units, develop a form of stratigraphy, and then we want to put the map on the right, which then was used by the team to inform them on, you know, these units are all the same, but these units are different. Here are their contacts are. So that was all done pre-landing. So we kind of started the mission before you even get to the mission in terms of being on the surface. So we know where to go when we land. So I always like to say time is science. We want to spend more time doing science and less time doing the engineering and figuring out where to go or how do you take an arm coordinate and put it onto the surface. And maps also served an incredibly important part in the landing, not just from a statistical sense of saying this, like the landing ellipse on the right, Sarah, this is black ellipse is, you know, where you can land safely 99%. But Jezero is a very rocky area, has lots of hazards. And so basically we need to use terrain relative navigation, which is a way that the rover can look at a map on board. And then with that is a map that shows the safety, the hazards, which you see on the right here, and then find out which pixel is actually safe to land in. So in this case, on the right, the blue areas are safe to land, yellow less so, red would be death, as they say. So importantly, the map is not just for a statistical inference of how safe it is. It was actually used on the spacecraft to land itself safely. And it did. So here's the landing location in that little green dot. And then below is where we landed in that map. You can see like it squeezed the rover just between two red areas and a nice little blue patch. So these maps were incredibly important and weren't just to say, we think it's going to be safe to land. We know it's where it's safe to land and we're going to go there. So then, it's not just about data from orbit. Again, we collect data on the ground and we want to bring all that data together. So you have, in images at different scales, right? You've got images top left, which are looking at hills that's tens of meters of tall. To the right, you're looking at a zoom in for an outcrop that's maybe a meter in scale. And then in the bottom left, you have these microscopic images, which are down to the centimeters to millimeters per scale, and even down to hundreds of microns. So that was Curiosity, same thing for Perseverance. And I just wanted to, besides fact, we're talking with a surface asset, which is always touching the ground. And then we have images in the lower left, which are from the helicopter, which we can kind of look at all those for context. And then just to show that we've started to think of the next Mars mission, which is Mars sample return. And that's the first sample tube that we've dropped on the surface. And we've actually just completed the contingency depot this past week. So pretty exciting. So Mars sample return has something to go get. But in terms of the mission, how do we answer a lot of questions that the science team has? We answer it with maps. So we can do things like, show me all the high-rise coverage for a Gale crater and whether it's black and white or color. Where's the rover? And we want to drill every 25 meters in elevation. Show me where those drill lines are in blue, so we can use it as a guide for when we should be collecting the next, drilling the next sample. We want to keep track of everywhere we've drilled, and we also want to be able to compare data on the ground and see how it changes, over time in elevation. So here's a map of drill locations and the Molly images of the drill after the drill, and those actually the colors of the debris that comes out from the drill, the cuttings, tell you something about basically the hydration state of these. So you see those ones are more red or more iron rich, or more acidic, and the blue ones are a bit more neutral in terms of their pH in general, in terms of their water content and how they acidified. Anyways, move on. It's probably stay away from science. It's probably good for me. But then we just generally want to know, the science team wants to know where the rover is, how we've progressed over time. So just situational awareness is very important in missions. And then we even want that situational awareness in terms of what do we do at these locations. So here's a target map, which we generate every day for both missions, which shows the general outcrop, both in a top-down view to the top left and an oblique view at the bottom. And then where did we have targets? What did we call them so we can track them with science data? And then what type of observation was done? Which instruments did we use? And then we can go all the way to, eventually publications where we're combining scientific observations and locations so that we can talk about the sites in either in a bigger context or get drilled down into here's the context. Now let me talk about this one rock, which has this awesome result. And there's mapping, again, because we have data on the ground, we can do kind of in situ mapping. So this is a map done by Larry Crumpler. He's also working on the Perseverance missions. This is from MER, going around Cape York and saying, basically as far as the rover can see, we can map at that scale, and determine geologic contacts and, develop models based on multiple observations as we drive along at the rover scale. And, all this feeds into Mars sample return. So it's not just planning where we are now, but using where we are now as a guide for the future and how where can we drive forward? And then where can we, in this case, where can we drop samples so that we can collect them later? So all these parts kind of get tied together. So it's not just a map that's for safety for landing. It's not just a map for doing a mission. It's a map that connects all, and then the future missions, it's a map that connects all those together. So, we talk about mapping and we always, kind of your first thought, I think, is a static map, but really we've moved beyond that. We are now into interactive interfaces that we can zoom in. So this is just an example from Gale Crater, just showing the rover traverse in white, The black dots are where the rover's been. The green dots are actually places where we've done science. And it's not just the one view. We really, as a geologist, you want to connect all these views. You want to connect the view that's kind of the top-down map view. You want to connect in situ views like we have on the left. We're going to know where observations occurred. I'm just going to skip ahead for time. We want to be able to click on points and actually look at their chemistry results. So we can make a quick decision like, oh, look at this area. It's got a ton of silica, or, oh, it has really high calcium in that point, and so on and so forth. So we want to get beyond just, it's not just seeing where you are, but also what data is there. And, we can map that in different ways. But importantly, MMGIS in our mapping software, we try to combine, here's a 3D view on the right. And that data basically you're seeing is being shared across all 3 views. So that is really, with missions, again, we want to save time for science and not for people trying to figure out where everything is. So we provide that in the software. It's not just a picture, a pretty view. It can be a lot of things. So in the top left, inside of the mission software, mapping software, we have a tool for measuring distances, and it automatically generates a profile, and it'll show that in a bit. We also care about angles from where we are, because a lot of times we are giving azimuths and elevations in terms of where we want to point cameras. So the tool in the upper left, the measure tool inside of MMGIS, allows us to show elevations and show angles. We can turn layers off and on and read values that are both described by a legend or raw values from the base map. We can show them in 2D and 3D. The bottom left, we're actually showing view sheds. So a lot of times, we drive to a location and you can have a mosaic and you may not know how far away that hill is in the mosaic, but with the viewshed tool, we can actually tell you how far away that is. And we can also predict, if I drive here, here's where I can see things. And we use this awful lot in planning. But then also about collaboration. So again, we talked about science team for Perseverance, and XMRs use it for geologic mapping. And we use this every day. So we've been using it recently for planning our next set of explorations on the top of the Jezero Delta. And, people mapped out where they thought outcrops were interesting. And here, we should stop here. And, oh, can we drive this way or that way? So we have a collaborative based mapping tool. And I don't show it here, but we actually can symbolize polygons and lines and points with actual USGS geologic units and, strike and dip symbols and inferred or the different variations of line types. So we've kind of built that into it so we can do true geologic mapping and collaborative geologic mapping, because these files that you make are shared across all the members of the science team. And we use it for missions, but we also use it for outreach. So it's not just internal, it's also external. So here's an example of the map of where Perseverance rover is, and we update this every day. Every time the rover moves, that map gets updated, as well as the maps that we use during the mission. You think about planetary mapping, like, is there a future? Well, there is, absolutely. So this software that you've seen here, the MMGIS, which is multi-mission geographic information system, we use it on Perseverance, we use it on MSL, we used it on InSight, the Mars helicopter uses it, but it's not just JPL. We use it, the Johnson Space Center is using it for the Artemis project to develop a Artemis geographic information system for doing future EVAs. Ames Research Center is using it for the Lunar Viper mission, which is going to the moon in a year or so. As was mentioned, ESA used it for the XMRs to begin their mapping project. So the software is really tied together, but more importantly, mapping is everywhere. People are realizing mapping is not just fun, it's not static, it's active, it's a participant in missions, and it becomes important to know where you are and where things happened.